Following our previous couple of sessions on functions, periodicity, etc., where my objective was not to give you a very formal digression on functions, but to just let you know some basic terminology associated with functions, what a function is, and downright rudiments associated with functions and some properties related. Of course, we would have to bounce back to function with greater details down the line once I have covered monotonicity, maxima, minima. Once we learn to investigate functions, that's when I would have to come back to functions to introduce some more finesse associated with functions. But for the time being, the basic idea that has been imparted to you would suffice. Now, another notion that I'm going to introduce to you today is the following. Suppose there is a collection of numbers, a sequence, commonly referred to as a sequence. Say x1 is 1 plus 1 by 1, x2 is 1 plus 1 by 2, x3 is 1 plus 1 by 3, xn is 1 plus 1 by n, and so on and so forth. This is a collection of numbers referred to as a sequence xn. Referred to as a sequence xn. Now, observe that as n becomes larger and larger and larger, 1 by n will become smaller and smaller and smaller. It then seems to us, and very believable, that xn, as n becomes larger and larger and larger, comes closer and closer and closer to 1, right? Now, what this really means is, that means, a statement like this, as n becomes larger and larger and larger, as n becomes larger and larger and larger, xn comes closer and closer and closer to 1, right? Now the statement is commonly put up as, limit xn as n tends to infinity is 1. Limit xn as n tends to infinity is 1. Now, the more technical meaning of this statement, is as follows. When I say that the limit of a sequence is 1, what it really means is that I can find a capital N. I can find a certain capital N. Such that for all n, small n greater than that capital N, for all small n greater than that capital N, the numerical difference between xn and 1, this is the numerical difference between xn and 1, for all n greater than a certain capital N, the numerical difference between xn and 1 could be made smaller than any positive number, no matter how small this epsilon is. Epsilon is a very small positive number. The difference between xn and 1 for all n greater than capital N could be made smaller than any epsilon, no matter how small this epsilon is. Right? That means, in this case, for example, and epsilon is my choice. I could select epsilon as 0.000001. I can select epsilon as 0.050,000 zeros and then 1. That means the difference between xn and 1, for all n greater than a capital N would be smaller than that epsilon. if I can cause that to happen for any epsilon, no matter how small that epsilon is, then I can claim that limit xn as n tends to infinity is 1. Which means, say someone selected a value of epsilon equal to 10 to power minus 4. Suppose somebody selected a value of epsilon equal to 10 to power minus 4. Now, xn minus 1 is what? 1 by n? Xn minus 1 is 1 by n. So xn minus 1, this I can write as 1 by n. Mod of that will also be 1 by n. 1 by n less than epsilon, which is 10 to power minus 4. Right? That means n greater than 10 to power 4. N greater than 10 to power 4, yes or no? That means if I select members of the sequence such that small n greater than 10 to power 4, small n greater than 10 to power 4, then all such members of the sequence xn would be such that the difference between xn and 1 would be less than 10 to power minus 4. If someone selected 10 to power minus 8, again a smaller number, right? Then n will become greater than 10 to power 8. That means for all small n greater than capital N, this capital N is 10 to power 8 then. The difference between xn and 1 will be less than 10 to power minus 8. 10 to power minus 8. Right? So I can keep selecting smaller and smaller values of epsilon. I can keep getting larger and larger values of capital N such that for all small n greater than that capital N, the difference between xn and 1 could be made smaller than any epsilon, no matter how small that epsilon is. Do you understand this fact? If I can cause this to happen for any epsilon, no matter how small that is, then I claim that the limit of the sequence as n tends to infinity is 1. That's the meaning of limit of a sequence. Loosely speaking, less technically speaking, it means that the difference between xn and 1 could be made as small as I want by selecting a small n larger than a certain capital N. No, that capital N will depend on the value of epsilon. See, when I select epsilon as 10 to power minus 4, that capital N becomes 10 to power 4. If I select that epsilon as 10 to power minus 8, that means for any epsilon, no matter how small it is, I'll be able to find a capital N such that, so this capital N will be a function of epsilon. Right? Then for all small n greater than capital N whose value depends on epsilon, the difference between xn and 1 could be made smaller than a certain choice of epsilon, irrespective of how small that epsilon is. For every small epsilon, I can find a capital N such that for all small n greater than capital N, this condition remains validated. Yes or no? Right? So this is the meaning of limit of a sequence. This is the meaning of limit of a sequence. Suppose, let me take another sequence. Suppose I have x1 as 1 minus 1 by 2, x2 as 1 plus 1 by 2 squared, x3 as 1 minus 1 by 2 cubed. So xn would be 1 plus minus 1 to power n by 2 to power n. Suppose this is a sequence. Suppose this is a sequence. Right? Now, prima facie, it does appear that as n becomes larger and larger, xn comes closer and closer to 1. Right? That means if that is indeed the case, that means if indeed limit xn as n tends to infinity is indeed equal to 1, then what it really means is that for any epsilon, of course greater than 0, no matter how small it is, one could find a capital N, such that for all n greater than capital N, the difference between xn and 1 could be made smaller than that choice of epsilon, right? And the value of capital N will depend on epsilon, how small I want to bring xn to 1, right? Say, which means now in this case, suppose somebody selected a certain value of epsilon, and you want to find if suppose I can find a capital N such that for all small n greater than capital N, the difference between xn and 1 is smaller than that epsilon, then I can claim that limit of xn as n tends to infinity is 1, right? Now, in this case, what is xn minus 1? Minus 1 to power n by 2 to power n, right? So come down to this. That modulus will eat up the minus 1 to power n. So all that you are left with is 1 by 2 to power n less than epsilon, right? Epsilon is given to us, which means 2 to power n will be greater than 1 by epsilon, or n log 2 greater than log 1 by epsilon. That means for all small n greater than, this becomes capital N. Capital N becomes log 1 by epsilon divided by log 2. For all small n greater than this number then becomes my capital N. For all small n greater than this capital N for that choice of epsilon, the difference between xn and 1 becomes smaller than epsilon. Isn't it? This becomes my capital N. If I select another value of capital epsilon, if I select yet another value of epsilon smaller than that, I'll get yet another value of capital N. But for all small n greater than capital N for a given epsilon, no matter how small it is, the numerical difference between xn and 1 could be made as small as I want. That's the conceptual meaning of limit of a sequence, right? Do you understand this then? Now, yeah, essentially what is it that you, but the point is epsilon should be made as small as you want. Is your choice. For every epsilon, no matter how small you choose, you will be able to find a capital N such that for all small n greater than capital N, the difference between xn and 1 is smaller than the choice of epsilon that you have made. For every such epsilon, you will be able to find a capital N such that for all small n greater than capital N, this condition is legal. Right? Okay. Now, from limit of a sequence, let me move to what is customarily referred to as limit of a function. Let's migrate to this. Once I have given you a warm-up on what limit of a sequence is, let me extend this idea to limit of a function. The most legal understanding of limit of a function. Now, suppose yes, This is the graph of a function y equal to fx x. Okay. This is x equal to a, and say this number is L. This length is L. This length is L. Now, I select a very small number epsilon. I'll be hovering around L. I'll be hovering around values of the function close to L. I would be hovering around values of function close to L, right? L plus something, L plus, let's say, 10 to power minus 10, and L minus 10 to power minus 10. That's when I say I'm in the neighborhood of L, right? Now, I select a very small value of epsilon, a very small value of epsilon, of course, positive, very small, and let's say the function, this is a value of the function which is L minus epsilon, epsilon smaller than L, this is the value of the function epsilon more than L, right? And epsilon is as small as one could imagine. That means essentially I'm trying to bring the value of the function as close to L as I want. Right? The smaller the choice of epsilon, the smaller the choice of epsilon, the closer the value of the function comes to L. Right? That's the whole idea. Now, this is the value of the function L minus epsilon. This is the value of the function L plus epsilon. Now, suppose there is a neighborhood around x equal to a. Suppose there is a neighborhood around x equal to a, delta units to the right of a and delta units to the left of a. Suppose there is a neighborhood around x equal to a, delta units to the right of a and delta units to the left of a, right? That means this is a plus delta and this is a minus delta. Delta units to the right of a and delta units to the left of a. That means we call it the delta neighborhood around x equal to a. We'll refer to this neighborhood as delta neighborhood around x equal to a. Such that in this delta neighborhood, delta neighborhood, the value of the function lies between L minus epsilon to L plus epsilon, such that the value of the function in this neighborhood lies between L plus epsilon and L minus epsilon. Right? If epsilon is very small, then the value of the function is very close to L. Yes or no? If epsilon is very small, the value of the function is very close to L. Right? The smaller the choice of epsa, the closer the function comes to L. The smaller the choice of epsa, the closer the function comes to L. Which means, now, the delta neighborhood, the size of the neighborhood on either side of x equal to a, delta neighborhood around x equal to a, right, will depend on choice of epsa, right? If I select one value of epsa, then the delta neighborhood around x equal to a will depend on epsa. That means what we are trying to do is, I've selected a value of epsa, very, very small. I've selected a value of epsa, very, very small. Now, the question is, can I select a neighborhood around x equal to a? After having selected an epsa, very small, right? Now the question to be addressed is, can I select a delta around x equal to a? Can I select a delta around x equal to a such that in this delta neighborhood around x equal to a, the value of the function remains confined to L minus epsa to L plus epsa? For a given epsa greater than 0, no matter how small if one can find a delta neighborhood around x equal to a such that in this interval, this condition is valid, fx greater than L minus epsa less than L plus epsa, such that in this interval, delta units to the right of a and delta units to the left of a, all the values of the function that you encounter in this neighborhood necessarily lies between L minus epsa to L plus epsa. And this delta will depend on our choice of epsa. Right? If I select one value of epsa, very small, I'll get one kind of a neighborhood around x equal to a, for which every value of the function that occurs in this interval will lie between L minus epsa to L plus epsa. Right? Delta very clearly then would be a function of epsa. If for every epsa a delta could be found, no matter how small this epsa is, if I can find a delta, then if this happens, we say limit fx x tends to a equals L. Limit fx x tends to a equals L. If epsa is very small, then realize fx is very close to L. Epsa could be, let's say, 10 to the power minus 100, right? Then the value of the function in that delta neighborhood would lie between L minus 10 to the power minus 100 and L plus 10 to the power minus 100. If for this epsa equal to 10 to the power minus 100, if I can find a certain delta such that in that interval of x, the function lies between L minus 10 to the power minus 100 and L plus 10 to the power minus 100. Again, I select another smaller value of epsa, say 10 to the power minus 1000, right? And I can find a delta for epsa equal to 10 to the power minus 1000, such that in that delta, the value of the function lies between L minus 10 to the power minus 1000 and L plus 10 to the power minus 1000. I select again a smaller value of epsa, 10 to the power minus 1 lakh. And even for that epsa equal to 10 to the power minus 1 lakh, if I can find a delta whose value will depend on epsa, such that the value of the function lies between L minus 10 to the power minus 1 lakh and L plus 10 to the power minus 1 lakh. Essentially, I'm able to select a neighborhood around x equal to a, wherein the value of the function could be brought as close to L as I want. Right? I can bring the value of the function as close to L as I want, notionally speaking, qualitatively speaking, right? If I can do that, no matter what, how close I want to bring fx to epsa, fx may actually never attain a value equal to L. Fx may never attain a value equal to L, but could be brought as close to L as we want. Fx may or may not ever attain a value equal to L, but if the value of the function in that neighborhood could be brought as close to L as I want, then we say limit of the function as x tends to a is L. If all of this happens, then we claim that the limit of fx x tends to a is L. That's no. The meaning of this statement is all of this. Please try and understand. For every epsa, I can find a delta. It's not that I'm trying to find epsa and delta. There is nothing like a fixed epsa and fixed delta. You select a value of epsa equal to 10 to power minus 1 crore. And for that, I can find a delta such that in that delta neighborhood, the value of the function lies between L minus 10 to power minus 1 crore and 10 to power plus 1 crore. Tomorrow you select a value of epsa equal to 10 to power minus 50,000 million. Right? For that also, if I can find a delta such that means essentially qualitatively, what are you trying to do? You are trying to bring the value of fx as close to L as you like by selecting smaller and smaller and smaller values of epsa. No matter how small epsa, if I am able to deliver a delta whose value will depend on epsa, that means I have a neighborhood around x equal to a within which for every small epsa, I have the value of the function lying between L minus epsa and L plus epsa. That means I'm successful in bringing the values of fx as close to L as I want by selecting smaller and smaller and smaller values of epsa. But then for that, I should have a value of x within which that must be satisfied. A minus delta to a plus delta, that is the delta neighborhood in which that condition would be satisfied. That's when I say limit fx x tends to a is L. This is what it means, right? This is the most technical definition of limits. This is the most technical definition of limits. Qualitatively, like I said, all of this boils down to in laymanish terms, fx brought as close to L as I want. Fx may or may not ever attain a value equal to L. And when I say limit fx x tends to a is L, it certainly does not mean that this is the value of the function at x equal to a. It doesn't necessarily mean that the function ever attains a value equal to a. All that it means is, equal to L. Equal to L. The function may or may not ever attain a value equal to L. But then, if its value could be brought as close to L as I want by a suitable neighborhood around x equal to a, then I can claim that the function has a limit L as x tends to a. This is the meaning of limit fx as x tends to a equal to L, right? This definition is commonly referred to as an epsa delta definition of limit. An epsa delta definition. The original manuscripts in calculus would be all around the epsa delta definition of limits. What has come down to you, percolated into you, is a very packaged and simplified version of limits, right? Say, for example, if I said limit 3x plus 2 x tends to 1 equal to 5. 3x plus 2 as x tends to 1 equal to 5. My fx is 3x plus 2 in this case. and the limit I claim is 5 at x equal to 1. That's the limit as x tends to 1, right? What it really means is that, well, fx, okay, now one more thing that you might want to bear in mind. If I say in the neighborhood this is, say, L, this is x equal to a, this is a minus delta, this is a plus delta, a delta neighborhood around x equal to a, in which the value of the function must lie between L minus epsilon to L plus epsilon, right? A delta neighborhood exists for every epsilon. A delta neighborhood exists such that in this neighborhood fx is less than L plus epsilon and is greater than L minus epsilon. If for every epsilon a delta neighborhood can be found, then we say that the limit of the function as x tends to a is L. Now this, in a more packaged version, in a more notational form, what does it mean? It means the numerical difference between fx and L does not exceed L. For any given x, for any given x, this is fx, this is fx, and realize the difference between fx and L, the difference between this length and this length will never exceed epsilon in this interval, isn't it? The difference between this length and this length, numerical difference between this length and this length for any x in this neighborhood will not exceed epsilon, right? So that means this statement is about saying the numerical difference between fx and L is less than epsilon. In the delta neighborhood, which can be found based on epsilon, the numerical difference between fx and L does not exceed epsilon, right? This statement is about the numerical difference between fx and L does not exceed epsilon in a delta neighborhood surrounding x equal to a on either side of x equal to a, right? Clear? Now coming down to this, so this was just like rewriting this statement as this. This statement is like this only, right? I mean, if I have to write this statement, this can be written as fx minus L less than epsilon and minus epsilon, which will bring us to this statement. Realize that? Now, this is fx, and if its limit is 5 as x tends to 1, then what it means is the numerical difference between fx and 5. This is the numerical difference between fx and 5. I can make it smaller than any epsilon that I want. I can make it smaller than any epsilon that I want. If there exists a delta neighborhood around x equal to a such that in the delta neighborhood around x equal to a, that means if the difference between x minus 1, x and 1 is less than delta, the delta neighborhood around x equal to 1. If I can find a delta, yes or no? Mod x minus a, again this neighborhood, you know that I'm talking of a plus delta and a minus delta. In this neighborhood around x equal to a, the difference between fx and L is smaller than epsilon. But realize that in this neighborhood, the numerical difference between x and a is less than delta. In this neighborhood, the numerical difference between x and a is less than delta, right? So if for every epsilon I can find a delta such that in this delta, the difference between fx and L is smaller than epsilon, then I say that the limit of the function as x tends to a is L, right? So okay, come down to this. Mod fx minus 5 is less than epsilon.
Why won't we take a mod of x minus a less than equal to delta? Because if it is equal to delta, then
that does not matter. Then I can select again a smaller value of delta. Delta is not, I mean, delta is just a notional entity. For every epsa, I'm finding a delta. So the numerical difference between fx and 5, I want to make smaller than epsa. The numerical difference between fx and 5 is smaller than epsa. Let me see what this leads to. What this leads to is, what is fx? Fx is 3x plus 2. This would mean 3x minus 3 is less than epsa. What this means is mod of x minus 1 less than epsa by 3 for a given epsa, right? Which means what? Which means the following. It means x minus 1 less than epsa by 3 and greater than minus epsa by 3. This means x less than 1 plus epsa by 3 and greater than 1 minus epsa by 3. Right? Which means this is x equal to 1, this is 1 plus epsa by 3, and this is 1 minus epsa by 3. In this neighborhood of x, the numerical difference between fx and 5 is less than epsa. That means in this neighborhood, you take any value of fx, in this neighborhood around x equal to 1, epsa by 3 to the right of 1 and epsa by 3 to the left of 1. This is at x equal to 1. This is 5, this is x, and this is fx. The numerical difference between fx and 5 could be made smaller than epsa, isn't it? It all started with this. That means in this neighborhood, the numerical difference between fx and 5 is less than epsa, right? That means for every epsa, I can find a neighborhood epsa by 3 to the right and epsa by 3 to the left of 1, such that the numerical difference between fx and 5 could be made smaller than epsa. In this case, what is delta? Delta is epsa by 3, which is a function of epsa, This is my delta. A delta neighborhood in this case turns out to be epsa by 3. For every given epsa, the required delta is epsa by 3. For every given epsa, the required delta is epsa by 3. So for a very small epsa that you have selected, you go epsa by 3 to the right of 1 and you go epsa by 3 to the left of 1. In that interval, the numerical difference between fx and 5 could be made smaller than epsa. Right? The delta in this case turns out, delta which I told you is a function of epsa. In this case, that turns out to be epsa by 3. For different functions, you will have different values of delta dependent on epsa, right? So then, since this condition is validated in this interval, we say fx could be brought as close to 5 as I want, right? And that's when I say limit fx, x tends to 1 is 5. Limit fx, x tends to 1 is 5. You got me? Now, realistically, this is not what we would deploy to obtain limits. This is very cumbersome. You know, the fathers of calculus, the exponents of calculus, this is how they obtained all limits. You know, the epsa delta definition. It is quite a challenge, even at higher levels of mathematics, to obtain a limit using epsa and delta is not an easy task. You know, what I gave to you is really a very, very simple version. But if the function gets more and more intricate, to obtain the limit of the function as x tends to a, using the epsa delta definition is going to be very challenging. And therefore, the whole business of limits got packaged for you and has come down to you in a very fluid form, very simple form, right? A set of rules, a set of theorems, a set of principles packaged together will help you bypass the epsa delta definition of limits and obtain the limits with ease. But few things that I again reiterate. When I say limit fx as x tends to a is L, it does not mean, number one, that the function has a value equal to L at x equal to a. It may or may not. Number two, the function may never become equal to L for any value of x. Number three, the value of the function could be brought as close to L as I want by a suitable choice of neighborhood around x equal to a. That for sure. In fact, when I say limit fx x tends to a is L, it may even mean sometimes that the function is not even defined at x equal to a. Yet it could be brought as close to L as I want. The function may be undefined at x equal to a, yet its limit may exist. For example, I could have had a function like I could say y equal to fx, same function, say 3x plus 2 when x is not equal to 1 is 3x plus 2 when x is not equal to 1 and is undefined at x equal to 1. Suppose this is a function which is even undefined at x equal to 1, right? The graph of this function is going to be this. If it was defined at x equal to 1, then this would be a point on the graph with coordinates 1, 5. X equal to 1 and y equal to 5. If it was defined at x equal to 1, then this would be a point whose x coordinate is 1 and y coordinate is 5. But it's undefined at x equal to 1, right? Yes or no? Right? So this is not a point on the graph of the function, right? Because the description of the function is 3x plus 2 only when x is not 1. So I put a kink here. This is not a point on the graph of the function. However, and therefore for sure the function never attains a value equal to 5, because this is certainly not a point on the graph of the function. But the value of the function, if this is x, this is fx, the difference, I can select a suitable neighborhood around x equal to 1, and in that neighborhood the numerical difference between fx and 5 could be made smaller than any epsa that I want. The value of the function could be brought as close to 5 as I want, even though it never attains a value equal to 5, even though it's not even defined at x equal to 1, yet the value of the function could be brought as close to 5 as I want, and therefore the limit of fx as x tends to 1 still remains equal to 5. Despite the function not even attaining a value equal to 5, despite the function not even defined at x equal to 1. Yes or no? Now, again, seeking a qualitative and a diagrammatic understanding of the thing. I could have had a function like this. This is a kink on the graph of the function. This is x equal to a. And this is not a point on the graph of the function, but say this length is L1. Say this length is L1. Okay. Now, this again is not a point on the graph of the function, but say this length is L2. This length is L2. This length is L2. And say this is the value of the function at x equal to a. This is the value of the function at x equal to a. That means this point P, just to avoid clutter, has coordinates. X would be a and y would be f of a. This is x equal to a and y is, this is f of a. This is a point. These are kinks, not points on the graph of the function. This is the value of the function at x equal to a. Say it exists. Say the function is defined at x equal to a and has a value equal to f of a, right? Say f of a is L. F of a is L. Right? Now, notice that the region to the left of a, the region to the left of a is referred to as a minus 0. A minus 0 is the region to the left of a, immediate left. A plus 0 is the region to the immediate right of a. Right of left of x equal to a and right of x equal to a. This is to the right of a and this is conventionally the region to the left of a. Now, look at the region to the left of a in this graph. Very close to a. When I talk of a region to the left of a means you're not going to move a kilometer to the left of a. You're going to hover around very, very close to a. That's what it means, right? Of course, on the graph, to maintain clarity, I would give you an accentuated view. This is x to the left of a. This is x to the left of a. This is not a point on the graph of the function. The function never attains a value equal to L1. The function never attains a value equal to L1. This is the value of the function at x, which is f of x. This is the value of the function at x, which is f of x, right? Now, realize that as x comes closer and closer and closer to a, from the region to the left of a, this means x coming closer and closer and closer to a from the region to the left of a, right? If x hovers in the left hand neighborhood of a, if x hovers in the left hand neighborhood, this is called the left hand neighborhood of a. If x hovers in the left hand neighborhood of a, then realize that the numerical difference between fx and L1 could be made as small as I want. Then the numerical difference, right? By bringing x close enough to a, I can bring the numerical difference between fx and L1 as small as I want. Yes or no? That means the value of fx could be brought as close to L1 as I want, right? Even though it never attains a value equal to L1, fx could be brought as close to L1 as I want by a suitable left hand neighborhood around x equal to a. By a suitable left hand neighborhood around x equal to a. Then what it really means is as x comes closer and closer to a from the region to the left of a, fx comes closer and closer to L1. fx comes closer and closer to L1. This means we write it as limit fx x tends to a from the region to the left of a is L1. Limit fx x tends to a from the region to the left of a is L1. This is called the left hand limit at x equal to a. This is called the left hand limit at x equal to a. Called the left hand limit at x equal to a, which is L1. Right? Similarly, so far so good, right? This is the region to the right of x equal to a, this part of the graph. This length is L2. L2. Right? I select points very close to a to the right of a plus 0. This is the region a plus 0. Right? Right hand neighborhood of x equal to a. This is called the right hand neighborhood of x equal to a. This is the value of the function fx. Right? Again, qualitatively, fx never attains a value equal to L2, but fx could be brought as close to L2 as I want. It could be made, say, L2 minus 0.00000, 50 crore zeros and then 1. It could be brought that close to L2, right? Or even closer than that, right? That means, in this case, as x comes closer and closer to a from the region to the right of a, as x comes closer and closer to a from the region to the right of a, fx comes closer and closer to L2, even though it never attains a value equal to L2. Even though it never attains a value equal to L2, it could be brought as close to L2 as I want, right? And these two statements are put together as limit fx x tends to a from the greater than a side is L2. Right? And this is like this was called the left hand limit at x equal to a. L2 is called the right hand limit at x equal to a. And in this case, realize that neither the left hand limit nor the right hand limit at x equal to a have anything to do with the value of the function at x equal to a, right? Yes or no? So then for sure this is a very general situation. The left hand limit is L1, the right hand limit is L2, and if the left hand limit is not equal to the right hand limit, we say that the function does not have a limit, right? So if in this case the left hand limit not equal to the right hand, LHL henceforth would mean left hand limit, right hand limit. If the left hand limit at x equal to a is not equal to the right hand limit, we say that the limit does not exist. We say that the limit does not exist. That means DNE does not exist henceforth. For the limit to exist at x equal to a, the left hand limit must be equal to the right hand limit. And in the event, if limit fx as x tends to a from the less than a side is equal to limit fx as x tends to a from the greater than a side, and say each equal to m, then we say limit fx x tends to a equal to m. This is what we say. If the left hand limit at a and the right hand limit at a both are equal to m, we make this consolidated statement, one single statement representing both of these. Limit fx x tends to a equal to m. And conversely, if someone says this, limit fx as x tends to a is L, it would mean this equal to m, it would mean this equal to m. Right? The limit does not exist.
A exists, but then
A तो थाक भाई वहाँ. Why would A not exist? A तो आचे ही. এটা লিমিটের ব্যাপার, লিমিট আছে কিনা, that's what we need to check. Of course, that's how, I mean, that's the definition of, that's building the subject. We say for the limit to exist, that means, you know, see, essentially, if you approach A from the region to the right of A, you cannot say that fx could be brought as close to L1 as you want. Say, if someone says, okay, give me a value of L1 by coming closer and closer to A, from the region to the right of A, give me a value of L1, which is L1 plus 10 to power minus 50. Will you be able to produce that value of fx? No, na? Or coming from the region to the left of A, someone says, give me a value of fx, which is L2 minus 10 to power minus 60. Will you be able to do that? No. That means it's not like you could come from the region to the right of A and make the value of the function as close to L1 as you want. Or you can come from the region to the left of A and make the value of the function as close to L2 as you want. You cannot do that. Right? So neither nor L2 are limits of the function. But I can say temporarily that the left hand limit at A is L1, right hand limit at A is L2. Yes, please, of course. Carry on. No, not at all. See, for example, of course not. That was my contention. See, when didn't I do that? That 3x plus 2, it was not defined at x equal to 1, yet the limit existed, and right? See? Of course not. See, for example, something like this. Hello? Say, this is a function. It's undefined at x equal to a. But this length is L. It's undefined at x equal to a, but its length is L. But by coming closer and closer to a from the region to the left of a, by coming closer and closer to a from the region to the left of a, I can bring the value of fx as close to L as I want. Even though it never becomes equal to L, it could be brought as close to L as I want. Similarly, by selecting values of x to the right of a, hello, by selecting values of x to the right of a, I can make the value of fx as close to L as I want, even though it never becomes equal to L. So it's undefined at x equal to a. It has a limit. Its left hand limit as well as the right hand limit exist. Right? Yes or no? Because a limit has nothing to do with the value of the function at x equal to a. Right? Aladache. Right. Right, did you get me? Say, for example, have I discussed the box function, the fractional part? Right now, why are you getting so noisy? Let me be the only one creating noise here. Okay? You remain sound. See, the graph of y equal to fx equal to box of x. Graph of y equal to fx equal to box of x. Clear? Between 0 and 1, including 0 but excluding 1, it assumes a value equal to 0. This is a kink. At x equal to 1, it jumps to a value equal to 1. Then it remains 1. At x equal to 2, it jumps to a value equal to 2. It remains equal to 2. 3. At 3, it jumps to a value equal to 3. Remains 4 till 4. And so on and so forth. Yes or no? Right? This is how it happens. Right? In a more general sense, if this is an integer I, this is another integer I plus 1, the neighboring integer to the immediate right, at x equal to I, box of x will be equal to I, isn't it? At x equal to I, box of x will be I. Between I and I plus 1, box x remains I. At I plus 1, it jumps a value equal to I plus 1 and remains I plus 1 for 1 unit of length to the right. Right? This is a part of this graph between two integers I and I plus 1. Yes or no? Clear? Now, look. This length is I units, whereas this length is I plus 1 units. Yes or no? Right? Now, do you see that if I select an x like this, to the immediate left of I plus 1, I select an x to the immediate, or what I do is say, to the left of I, it will be I minus 1. Isn't it? Y would be I minus 1. Isn't it? At x equal to I, it becomes I. To the immediate left of I, the value of the function is going to be I minus 1. Isn't it? To the immediate right of I, the value of the function is going to be I. Right? Now, if I select an x to the immediate right of I is an integer. Right? As x comes closer and closer to I, as x comes closer and closer to I from the region to the right of I, as x comes closer and closer to I from the region to the right of I, do you realize that fx, this is my fx, this is my fx, fx comes closer and closer and closer and closer and closer and closer to I only, right? So the right hand limit at x equal to I will be I. Yes or no? So in this case, limit box fx, which is box of x, as x tends to I from the greater than I side, is going to be I. Right? The right hand limit at x equal to I is I. Yes or no? If I select a value of x to the immediate left of I, this is my fx. As x comes closer and closer to I from the region to the left of I, as x comes closer and closer to I from the region to the left of I, realize that fx could be brought as close to I minus 1 as I want. So we say fx comes closer and closer to I minus 1. Yes or no? And these two statements mean limit fx, x tends to I from the region to the left of I is going to be I minus 1. So this is the left hand limit at x equal to I. That's the right hand limit at x equal to I. And the two are unequal. So which means limit fx, x tends to I does not exist. Does not exist. Why? Because the left hand limit is I minus 1. The right hand limit is I. So for any integer I, the limit of box x as x tends to I does not exist. Does not exist. Yes or no? Right? Right? And in fact, if x is not an integer, say if x is not an integer, x is between two integers then? Say x is between two integers, right? Say for example x lies between 2 and 3, right? Then this length is 2 units. Then realize that this is a equal to 2. This is a equal to 2. Then at a equal to 2, the limit will exist. The left hand limit, as x comes closer and closer to a from the region to the left of a, box x comes closer and closer to 2. As x comes closer and closer to x equal to 2, box of x comes closer and closer to 2. So the left hand limit of this function is 2. The right hand limit is 2. Right? When a is, sorry, is a, this is some a lying between 2 and 3. This is not 2, so sorry. This is not 2. This is some a lying between 2 and 3. So if a is not an integer, the left hand limit in this case, for example, is 2. The right hand limit is also 2. The limit exists. Right? So for box of x, limit box x as x tends to I, where I is an integer, does not exist. Whereas limit box x tends to a, where a lies between two integers, but is not an integer, x tends to a, limit box x, this exists. Because if a lies between I and I plus 1, then in this entire neighborhood, box of x will be I. If a is a number lying between I and I plus 1, then on either side of a, the value of box x will be I. Then, isn't it? If a lies between I and I plus 1, then in the entire neighborhood around x equal to a, box x will be identically equal to I. Box x will be identically equal to I if a is a number lying between I and I plus 1, right? Say a is 2.3, then in that entire neighborhood around 2.3, box of x will be equal to 2. Box of x will be equal to 2. Yes or no? Right? And the limit will exist. That means in a neighborhood surrounding x equal to a, box x will be a constant function. For every constant function, the limit is equal to the value of the function only. For every constant function, the limit is equal to the value of the function. So around x equal to a, if a is not an integer, around x equal to a where a is not an integer, box of x will be constant and will be equal to I. Box of x will be constant and will be equal to I if a lies between I and I plus 1, and limit of box x then as x tends to a will be equal to I. The limit will exist when a is not an integer, but when a is equal to I, an integer, the left hand limit will be different from the right hand limit. Limit will then not exist. Clear? Similarly, check on this. Function y equal to fx equal to fractional part of x. I've drawn the graph of this function for you, right? Between 0 and 1, between 1 and 2, these are all kinks. This is the graph of fractional part of x, right? Now I is an integer. Do you realize this length is 1 unit? The function never attains a value equal to 1, right? This is an x, this is an x to the immediate left of I. This is an x to the immediate left of I, right? Do you realize that as x comes closer and closer to I, as x comes closer and closer to left of I, closer and closer to I from the region to the left of I, this is fractional part of x. For any given x, this is fractional part of x, yes or no? This will be fractional part of x. Fractional part of x comes closer and closer and closer and closer to 1, right? Even though it never becomes equal to 1, it could be brought as close to 1 as I want, right? So we say limit of fractional part of x, x tends to y from the region to the left of I is 1. Similarly, if x is to the immediate right of I, this would be fx. For a given x, this would be fractional part of x, right? As x comes closer and closer to I from the region to the right of I, fractional part of x comes closer and closer and closer and closer and closer to 0, right? So as x tends to I from the region to the right of I, fractional part of x comes closer and closer to 0. We write this as limit of fractional part of x as x tends to I from the greater than I side is 0. Yes or no? That means for any integer I, limit of fractional part of x as x tends to y does not exist. DNE. Why? Because the left hand limit is 1, the right hand limit is 0, the left hand limit therefore not equal to the right hand limit at x equal to y. The limit therefore does not exist for an integer I, for any integer I, right? However, if you select a value of a, x equal to a, which is not an integer, this is an a which is not an integer, then realize that the left hand limit at a will be this, the right hand limit at a will also be this. The limit will therefore exist. The limit will therefore exist, right? Yes or no? Right? So fractional part of x will not have a limit at a equal to an integer, will have a well defined limit when a is not an integer. Clear? Now certain things, something like limit 1 by x as x tends to 0. This limit we say is not finite. This is not a finite limit. Not a finite limit. Whereas limit x by x, x tends to 0, that's equal to 1, and this is a finite limit. See, in this case, the function is not defined. The function is x by x. It's not defined at x equal to 0. Do you realize that? Right? If I have to draw the graph of this function fx, which is by x, This will be equal to 1 when x is not 0. Yes or no? This will be equal to 1 when x is not 0, but will be undefined at x equal to 0. Right? So if I have to draw the graph of this function, what would be the graph of this function? The graph of this function is going to be at x equal to 0, there is a kink. To the right of 1, it remains 1. To the left of 1, it remains 1. Right? The function never attains a value equal to 1. But the right hand limit at 0 would be 1. The left hand limit at 0 will also be 1. This length is 1 unit. The limit exists. The limit exists even though the function is undefined at x equal to 0. And undefined at x equal to 0. Right? Because in finding the limit, I am not trying to find the value of the function at x equal to 0. I am certainly not trying to find the value of the function at x equal to 0. Right? There could be times that a function has a Chinese mustache. No mustache, right? It doesn't have a neighborhood around x equal to a. Look. Around x equal to a, it's all undefined. वो सांप खा खा के उसका मुंह छोड़ गया. Chinaman, right? So if a function doesn't have a neighborhood around x equal to a, then it doesn't have a limit also at x equal to a. Because you have to come closer. The function may have a value at x equal to a. One small piece of mustache at x equal to a. The chinku guy could have. But, so that could be say L. But, essentially to find the limit, you are not seeking to find the value of the function at x equal to a. You are seeking to find around x equal to a. You are coming closer and closer and closer to a, from the region to the right of a and from the region to the left of a. But there is no region on either side of x equal to a. And it's not like you can come from here. You have to come closer and closer to a, from the region to the immediate right of a and to the immediate left of a. The function may be defined further down, but in the immediate neighborhood, if it's not defined, then the limit does not exist, because there is no neighborhood. Limit is about the neighborhood. The entire concept of calculus is a social concept. More than what's happening at x equal to a, it's more about what's happening around x equal to the neighborhood, right? That's when sometimes I feel, deep down, if Newton got this entire idea of calculus right, bothering more about the neighborhood than what's happening, it must have had something to, he must have read the Indian scriptures very well to understand the social system of our land too good. That's where he would have got inspired to come up with this brilliant idea of calculus, which is more about the neighborhood than what's happening at x equal to a. Right? Sorry? All? You who know it better than you. And in any case, you keep your influence in the neighborhood very strong, because you have so many messengers, chutku putku messengers. You throw them all around in the neighborhood. Ja beta pata laga gaya. Ja beta pata laga gaya. Paas mein kya ho raha hai? Right? Sorry, after a long time. Got me, huh? So this business of calculus is very Indian, very indigenous. And therefore we Indians are very good at calculus. Trust me, we are the best on the planet in calculus, because it's exactly related to our brought up and our social surroundings. Right? Okay. So far so good, right? Now, so like I said, the epsa delta understanding to evaluate limits is a terse notion, very terse notion. To simplify matters for you, certain rules have been defined, certain standard limits have been obtained, right? Based on an interplay between these certain rules and these standard limits, we evaluate other limits of functions if they exist. So, certain rules say fx and gx are two functions. And say limit fx x tends to a is L. Limit fx x tends to a is L. And say limit gx x tends to a is M. And say L and M are finite numbers. That means both these limits are finite. That means both these limits are finite. Then I can say the sum difference rule, f plus minus g, limit of the sum or difference. This is limit of the sum or difference. That will be equal to sum or difference of the limit. Limit of the sum or difference would be sum or difference of the limits, provided both limits exist and are finite. Provided both limits exist and are finite. Similarly, limit of the product is product of the limits again provided both limits exist and are finite. I mean, see, for example, if I had limit x into 1 by x as x tends to 0, right? This is product of two functions, f which is x, g which is 1 by x. I can't write this as limit x as x tends to 0 into limit 1 by x as x tends to 0. Why? Because this limit is not finite. This limit is not finite, right? So this is wrong. Limit of the product will be product of the limits when both limits exist and are finite. In this case, limit 1 by x as x tends to 0 is not finite. So this is incorrect. This is incorrect, right? Suppose, and then look at the quotient rule. Limit of the quotient will be quotient of the limits only provided both limits exist and are finite. In this case, there is an additional condition. It's not enough for both L and M to be finite. It's also important that the denominator limit not be 0. So in this case, an additional condition is required. Limit g as x tends to a should not be equal to 0. Should not be equal to 0. Limit g as x tends to a should not be 0. In other cases, it could be 0. But in this case, since it appears in the denominator, the limit of the denominator should not be 0. I mean, realize that again, coming back to the same thing, limit x by x as x tends to 0 cannot be written as limit x tends to 0 divided by limit x as x tends to 0. Why? Because this becomes 0. So this is not right. Limit of the quotient would be quotient of the limits, provided both limits exist, both limits are finite, and the denominator limit is not 0, and the denominator limit is not 0. Do you understand that? So far so good, right? Now see, there is something about tending to 0 or tending to or being identically 0. Tending to 0 and being identically 0. See, say if I have limit x by x as x tends to 0. In this case, numerator and denominator both tend to 0. They are not equal to 0, they tend to 0, right? This limit is 1, right? It's not like I can plug in x equal to 0, right? They are tending to 0, they are not equal to 0. In contrast, suppose if I had limit box x by x, x tends to 0 from the greater than 0 side. See, this is important to understand. X tends to 0 from the greater than 0 side. Now what really it means is, see, when x is to the immediate right of 0, when x is to the immediate right of 0, box x is identically 0. Box x is identically 0. To the immediate right of x equal to 0, box x is identically 0. It's not tending to 0. Box x is identically 0. Right? If it's identically 0, you can plug in 0 here. If it's identically 0, this is like, it's not tending to 0, to the immediate right of 0. Let's say x equal to 0.33, etc. Box x would be identically 0, and this would be limit 0 as x tends to 0 from the greater than 0 side, and this will be 0. If it's identically 0, you can plug in that value of 0 in the neighborhood of x equal to 0. If it is identically 0, you can plug in 0. In this case, in the neighborhood of x equal to 0, this x is not identically 0, or this x is not identically 0. So you can't plug in 0 here. But in that case, it is identically 0. This limit, the right hand limit is 0. So to the immediate right of x equal to 0, box x is 0, and that will give me, I can therefore plug in box x equal to 0 here and obtain the limit, right? If I want limit box x by x, x tends to 0 from the less than 0 side. Now when x is slightly less than 0, box x is identically minus 1. It's not tending to minus 1, it is identically minus 1. So then I can plug in minus 1 by x. X tends to 0 from the less than 0 side. This is not finite. This is not finite, and we say the left hand limit does not exist. The left hand limit does not exist. Because it's not finite, we say the left hand limit does not exist. Even when the limit is not finite, we say the limit does not exist. So the left hand limit is not finite, we say the limit does not exist. The right hand limit exists and is equal to 0. To the immediate left of x equal to 0, no matter what x is, box x is identically minus 1. So replace box x by minus 1. As x tends to 0 from the less than 0 side, this does not tend to a finite number. If x becomes smaller and smaller and smaller, this becomes larger and larger and larger numerically. So right? So it's not finite. If it's not finite, then also we say it does not exist, right? Yes or no? Say limit x squared minus 9x plus 20, right? X minus 5, x minus, say, box x tends to 5. Suppose I want to evaluate this. X tends to 5. I want to evaluate this limit, right? X tends to 5. I want to evaluate this limit. Now, to the immediate left of 5, box x is identically 4. To the immediate right of 5, box x is identically 5. Therefore, then we get polarized here. We talk of a region to the left of x, left of 5. We talk of a region to the right of 5 because they're distinctly different in behaviors, right? So then, I write this as the left hand limit x tends to 5 from the less than 5 side. Left hand limit at x equal to 5. Region to the left of x equal to 5. This I write as x minus 4 into x minus 5. Right? The numerator could be written as x minus 4 into x minus 5 divided by. Now when x is slightly less than 5, box x is 4. Identically 4. Since it's identically 4, I can plug in the value. Right? So this is like x minus 4. Now I can cancel x minus 4 from both sides, from numerator denominator. So this will become 0. So the left hand limit at 5 turns out to be 0, right? This is the left hand limit at x equal to 5. Now let me talk of the right hand limit at x equal to 5. That means limit x tends to 5 from the greater than 5 side. Numerator again factorized. X minus 4 into x minus 5 divided by. Now when x is slightly greater than 5 and that entire neighborhood to the right of x equal to 5, box x is identically 5. It's not tending to 5, it's identically 5, and therefore I can plug in 5 here.
In that case, we couldn't cut x by x. So how can we cut x minus 4 and from numerator?
No, why couldn't we cut? We could cut, we did cut. That's how we got 1. We did cut. We did cancel. See, because x tends to 0, it's not equal to 0. Therefore, I can cancel. Alright? Because I'm not trying to find the value at x equal to 0. Therefore, it's not what's happening at x equal to 0. Right? It's only undefined at x equal to 0. But not in the neighborhood of x equal to 0. Right? So, in this case, this gets cancelled. So, this becomes 1. So, the left hand limit at 5 is 0. The right hand limit is 1. The limit therefore does not exist. Limit therefore does not exist. Yes or no? Right? So far so good, right? Now, one of the things which is not allowed while I'm talking is your talking, right? Although I was about to talk more about limits. What is not allowed is, suppose I had x squared minus 1 by x minus 1 as x tends to 1, right? What is not allowed is a partial behavior towards this, your partial response. You can't say, okay, as x tends to 1, I can put this equal to 1. So 0 by x minus 1 as x tends to 1. This is not allowed. You will have to deal with this holistically, not partially. This is partially. I mean, you thought, okay, I'll deal with the denominator later. Let me just put x equal to 1 in the numerator, 0, and by x minus 1, since x does not tend to 1, it is going to be 0. X is not equal to 1, so this is not 0, this is 0, so this will be 0. You can't do this, right? As beginners, you might be liable to such traps, right? So stay away from such vulnerabilities, okay? These are all the things that students have taught me when they have done this, okay?
Sir, but we cannot put the value because it's tending to 1.
Arey Baba, that's exactly what I'm saying. No, in certain cases you can. You say, okay, I will not put the value 1 in the denominator, but in the numerator I'll put 1. Denominator pore dekha jabe. Right? So you can't do this. Okay. Now, so far so good, right? Now, to evaluate limits, there are certain principles again that will come in very handy. One of them is what's called the sandwich theorem. The sandwich theorem. Cucumbers, tomatoes, cheese and butter, with some bread, of course, right? Say fx is a function around x equal to a, around x equal to a, in the neighborhood of x equal to, means very close to x equal to a, right? Immediate vicinity of x equal to a. fx satisfies this condition. Fx is sandwiched between two functions, Lx and ux. Only in the neighborhood around x equal to a, fx is sandwiched between two functions. Fx is always greater than or equal to Lx. Fx is always less than or equal to ux. In the neighborhood of x equal to a. Then we say in the neighborhood around x equal to a, this is like a lower bound function. This is called an upper bound function. This is called the sandwiched function. This is called the sandwiched function. And if it so happens that limit of the upper bound function, limit ux as x tends to a, is L, limit of the upper bound function at x equal to a is L, and limit of the lower bound function at x equal to a is L, then we say that the limit of fx, the sandwich function, will also be L. Then the limit of the sandwich function will also be L. In the sense, of course, without offering any formal proof, just to make the assertion kind of believable, in the xy plane I draw the three functions. This is the upper bound function, say. This is the lower bound function. This is x equal to a, and say this is fx. This is the graph of y equal to fx, which is sandwiched between the lower bound function and the upper bound function. So if the lower bound function tends to L, if the upper bound function tends to L, then the sandwich function will also tend to L as x tends to a. As x tends to a. This is called sandwich theorem. I'm not offering a proof for this, it's not required, but it's a powerful theorem. It's a very powerful theorem, right? Say for example, there is a function fx which is less than or equal to root 9 minus x squared and is greater than or equal to root 9 minus 2x squared around x equal to 0. Around x equal to 0, there is a function fx less than or equal to root 9 minus x squared and greater than or equal to 9 minus 2x squared. Around x equal to 0, right? And I want to find limit fx, x tends to 0. I want to find limit fx as x tends to 0, right? Clear? Now, limit root 9 minus x squared, the upper bound function as x tends to 0, will be 3. Right? Limit root 9 minus 2x squared as x tends to 0 will also be 3. That means the lower bound function tends to 3. The upper bound function tends to 3. Therefore, fx must also tend to 3. So we can conclude from this, we can conclude that limit fx x tends to 3, x tends to 0 must also be 3. Must also be 3. Right? Suppose, can I wipe this off? Right? Suppose I have limit mod x sine 1 by x as x tends to 0. Suppose I want to find limit mod x sine 1 by x as x tends to 0. Now, mod sine 1 by x will always be less than or equal to 1. Right? Will always be less than or equal to 1. And of course, greater than or equal to 0. Mod x sine 1 by x will always be greater than or equal to 0, less than or equal to mod x multiplying by mod x throughout. Right? Now, as x tends to 0, mod x will tend to 0. Right? This is the upper bound function. This tends to 0. As x tends to 0, the lower bound function 0 will also tend to 0. The upper bound tends to 0, the lower bound tends to 0. Right? Therefore, the sandwiched function will also tend to 0. Will be 0. If the modulus of a number tends to 0, then that number will also tend to 0. This would actually mean x sine 1 by x as x tends to 0 will also be 0. If the modulus of a number tends to 0, that number must also tend to 0. Right? So, limit x sine 1 by x, x tends to 0 will be 0. Even though as x comes closer and closer to 0, 1 by x becomes larger and larger and larger, but sine 1 by x will always lie between minus 1 and plus 1. Therefore, this will be a finite number. This will come closer and closer to 0. So this whole thing will come closer and closer to 0. So the limit of this will be 0. That's another way to look at it. Right? Suppose b greater than a greater than 0. B and a are two real numbers, b greater than a and a greater than 0. Okay. Let me look at fn a to power n plus b to power n whole to power 1 by n. Right? Now, if b is greater than a, very clearly b to power n will be greater than a to power n. Yes or no? B to power n will be greater than a to power n. N, let's say, is a natural number and n is made larger and larger and larger. N is made larger and larger and larger. Okay. Now, can I say this? A to power n plus b to the power n. Adding b to power n on both sides will be less than 2b to power n. Can I say this? Yes or no? But this, since a to power n is positive, this will always be greater than b to power n for sure. Yes or no? This obviously will be greater than b to power n because this is a positive number, but will be less than 2b to power n. Which means a to power n plus b to power n whole to power 1 by n would be less than 2 to power 1 by n into b and will be greater than b, raising both sides to power 1 by n. Now, as n tends to infinity, 1 by n becomes smaller and smaller and smaller. So this will tend to 0. So this will tend to 1. 2 to power 1 by n will tend to 1. So this will tend to b. Tends to b. As n tends to infinity, this is also tending to b. Right? As n tends to infinity, this will tend to b. This is also tending to b. And therefore, from sandwich theorem, this will also tend to b. Because the upper bound function tends to b, the lower bound function tends to b. So, can I not say a to power n plus b to power n whole to power 1 by n when b is greater than a? As n tends to infinity, from sandwich theorem will be equal to b. Right? Yes or no? Of course, we could have done this without sandwich theorem, but since I am illustrating sandwich theorem, see, if I take limit n tends to infinity, a to power n plus b to power n whole to power 1 by n, b larger than a. Let me take b to power n common from this. Right? Now, a by b is greater than 0 but less than 1 because b is larger than a and both positive. Right? So, can I say that as n tends to infinity, if you raise a by b to a larger and larger power, this will tend to 0. Say, suppose this is 0.3. 0.3 to a larger and larger and larger and larger power will make it smaller and smaller and smaller. Yes or no? Right? So this will tend to 0 as n tends to infinity. Right? This will be 1. This will be 0. 1 to power 0. 1. So this will be B. This will be B. Right? So far so good? Now suppose I have a sum Sn which is n by n square plus 1 n. Right? And I seek to find limit Sn as n tends to infinity. And I seek to find limit Sn as n tends to infinity. Now do you realize, of all these n terms, this is the largest because its denominator is the smallest, and this is the smallest because its denominator is the largest. Right? Do you realize then that each term here is less than or equal to this? Right? Yes or no? So can I say Sn is less than n times the largest? There are n terms here. Sn would be n times less than n times the largest? Can I say this? No? Didn't understand. N by n square plus 1 is equal to n by n square plus 1. Right? N by n squared plus 2 would be less than n by n squared plus 1. N by n squared plus 2 plus 3 would be less than n by n squared plus 1. N by n squared plus n would be less than n by n squared plus 1. Yes or no? So if I add these, this is Sn would be less than n times this. Yes or no? Yes or no? This is sum of n terms. It will be less than n times the largest, isn't it? But will be greater than n times the smallest. Isn't it? It didn't require me to do this. Okay? So this is going to be, Sn would be greater than n times the smallest. The smallest here is n by n square plus 1. Yes or no? Plus n. N squared plus n. How about it? Right? Now that means Sn is less than, dividing numerator denominator by n squared, 1 by 1 plus 1 by n squared, right? And is greater than 1 by 1 plus 1 by n on dividing by n squared. Yes or no? Right? As n tends to infinity, 1 by n squared would tend to 0. So this tends to 1. Yes or no? As n tends to infinity, this tends to 1 because 1 by n tends to 0. Therefore, as n tends to infinity, Sn tends to 1 out of sandwich theorem considerations, right? So this would mean limit Sn n tends to infinity is 1. Right? Let me. So far so good? Clear? Say A is a positive real number, right? Say A is a positive real number. If it's a real number, it'll either be an integer p or will lie between two integers p and p plus 1, right? If it's a positive real number, it'll either be an integer p or would lie two integers p and p plus 1. A is a positive real number, p is an integer, it'll either be the integer or will lie between two consecutive integers p and p plus 1, right? Right? Now n is a natural number, n is a natural number. I now want to find limit a to the power n by n factorial n tending to infinity. I want to find limit a to power n by n factorial where n tends to infinity. Now, do you realize a to power n by n factorial is actually a to the power p, a to power n minus p, this n factorial, p factorial, and then p plus 1, p plus 2, up to n, yes or no? See, this is 1 into 2 into 3 into p, then p plus 1 into p plus 2 up to n. That will make it n factorial, and a to power n I can write as a to power p into a to power n minus p. Can I do that? And this n is actually what? P plus n minus p is this n? This n is p plus n minus p, yes or no? So this can be written as a to the power p by p factorial a to power a by p plus 1 into a by p plus 2 into a by p plus 3 a by p plus n minus p. Can I do this? Yes or no? See, there are n minus 1, n minus p a's, and there are n minus p terms here, 1, 2, 3, n minus p. So I paired them, one a with p plus 1, another a with p plus 2, another a with p plus 3, the n minus pth a with p plus n minus p, right? Right? Of these terms, which is the largest? A by p plus 1. Right? This is the largest. A by p plus 1 is the largest. So can I say this is like a to power p by p factorial. This is less than a to power p by p factorial into a by p plus 1 whole to power n minus p. Tell me if you understand this. Right? Okay. Do you understand this? Huh? Because this is less than or equal to a by p plus 1. This is less than a by p plus 1. This is less than a by p plus 1. This is less than a by p plus 1. So this product will be less than a by p plus 1 whole to power n minus p. Yes or no? Right? But so this is all about a to power n by n factorial. But this is greater than 0 because A is positive, N is positive. This will be greater than 0, right? Now, A is less than P plus 1. So, A by P plus 1 must be less than 1 and of course greater than 0. This is a number lying between 0 and 1. Now, as N becomes larger and larger, N minus P will become larger and larger, right? So, as N becomes larger and larger, N minus P will become larger and larger, right? This is a number less than 1. This is a number less than 1. And this power is raised, is made larger and larger and larger. So what happens to this? This will become smaller and smaller and smaller. Yes or no? Therefore, as n tends to infinity, this will tend to 0. As n tends to infinity, this will tend to 0. And therefore, as n tends to infinity from sandwich theorem, this will also tend to 0, right? So, as n tends to infinity, this fellow tends to 0. As n tends to infinity, this tends to 0. As n tends to infinity, therefore, a to power n by n factorial as n tends to infinity will also tend to 0, will also tend to 0. Right? So this again, this is one limit that I want you to remember. If a is a positive real number, limit a to power n by n factorial as n tends to 0 will be 0. See, essentially what is happening, you know, internally, as n is becoming larger and larger, this is becoming larger and larger. This is n factorial is also becoming larger and larger. But the truth of the story is that n factorial is increasing faster than a to power n. That is what is happening. This is also becoming larger and larger. This is also becoming larger and larger. But the denominator is increasing faster than the numerator. Consequently, the ratio is becoming smaller and smaller. This is what is happening deep down. Right? Limits. Some standard limits. Now, see, this is a circular arc centered at O and of radius R. Circular arc of centered at O and radius R. Okay. This is a rotating line OP that makes an angle theta radians at the center. That makes an angle theta radians at the center. Okay. At A, I draw a tangent to this circle. This point is Q. This point is Q. OP intersects, OP produced intersects the tangent at A. Right? This of course is 90 degrees. Radius perpendicular to the tangent. Right? This is a chord AP. This is a chord AP, right? This is R. This is R. And AQ is R tan theta, as you can see. AQ is R tan theta, right? Now realize that area of sector OPA, see the sector OPA, area of sector OPA is greater than area of triangle OPA, greater than area of triangle OPA, and is less than area of triangle OAQ. Can I say this? Area of the sector OPA will be greater than area of triangle OPA, but will be less than triangle OAQ. Can I say this? Okay. Now, what is the area of triangle OAP? Half the product of any two sides into sine of the included angle. Half of R into sine theta. That's the area of this triangle, right? So, area of triangle OPA is half of R squared sine theta, half of R squared sine theta, half AB sine C, right? Area of sector OAP is half R squared theta, area of the sector. If theta is in radians, R is the radius. Theta is in radians and R is the radius, then that's the area of the sector, right? Which is less than area of triangle OAQ. Half of R into R tan theta, half base into altitude, half of R into R tan theta. Right? So this would mean theta greater than sine theta less than tan theta. Yes or no? This is what it means. This would also mean 1 less than theta by sine theta. Theta is in radians, less than 1 by cos theta on dividing by sine theta throughout. Right? Now, as theta becomes smaller and smaller and smaller, cos theta comes closer and closer and closer to 1. So 1 by cos theta will also come closer and closer to 1. Right? So limit 1 by cos theta as theta tends to 0 is 1, and limit 1 as theta tends to 0 is also 1. Right? Sandwich theorem. Limit of this as theta tends to 0 is 1. Limit of this as theta tends to 0 is 1. So limit theta by sine theta as theta tends to 0 will also be 1. This would mean limit theta by sine theta as theta tends to 0 is 1. That's out of sandwich theorem. That's out of sandwich theorem. And of course, if this is 1, we can also say, and by the way, theta is greater than sine theta. Theta is numerically greater than sine theta. So that's another important inequality. Theta bigger than sine theta is an important inequality, right? You must remember this. So this would also mean limit sine theta by theta as theta tends to 0 is 1. Limit sine theta by theta as theta tends to 0 is 1. Clear? This would also mean, can I wipe this off? Limit x by sine inverse x as x tends to 0, x is in ray, is also 1. Why? Say put x as sine theta. Then what would this become? As x tends to 0, theta must also tend to 0. So going into the theta domain, 0, this x is sine theta. Sine inverse x would be theta, which is 1. So x by sine inverse x or sine inverse x by x as x tends to 0 will also be 1. Right? This would also mean limit tan theta by theta as theta tends to 0 is limit sine theta by theta into 1 by cos theta as theta tends to 0. Now in this case, this is product of two limits. Why? Because this limit exists and is finite. This is 1. This limit exists and is finite is 1. Therefore, limit of the product will be product of the limits. So this is 1 into 1. That's going to be 1 because both limits exist and are finite. So limit tan theta by theta as theta tends to 0 is also going to be 1. And similarly, theta by tan theta as theta tends to 0 and theta is in radians is also 1. The important thing is see what I got was x bigger than sin x numerically and less than tan x, right? That means very close to x equal to 0, very close to x equal to 0, x will be larger than, numerically larger than sin x, right? In fact, if I have to draw the graph of y equal to sin x by x, if I have to draw the graph of y equal to sin x by x, what we've obtained is limit of sin x by x as x tends to 0 is 1, right? Even though it's undefined at x equal to 0, it has a limit at x equal to 0 which is 1. There is a kink at x equal to 0 because the function is undefined. This is a kink. And as x tends to infinity, sin x by x would tend to 0. As x becomes larger and larger, sin x will be a number lying between -1 and 1, finite, and this will become larger and larger, so sin x by x will tend to 0. And not only that, sin x by x becomes equal to 0 every time x is plus minus pi, plus minus 2 pi, plus minus k pi in general, right? Right? The graph of this will look like this. It will tend to 0 as x tends to infinity. At x equal to 0, pi, 2 pi, 3 pi, etc. sin x will become 0. And the sign of sin x by x, if x is positive, the sign of sin x by x will be the same as sign of sin x, right? So these signs maintained, and the amplitude will go on decreasing because of x, right? This has an amplitude 1. As you go on increasing, its amplitude will go on decreasing. Not only that, this is y at x, which is sin x by x. Do you realize that y at minus x will be the same as y at x? Sin x by x will be the same as sin minus x by minus x, right? And therefore, whatever you've got for x, the same value of sine x by x you'll get for minus x. This is the graph of sine x by x. This is the graph of sine x by x. Its amplitude goes on decreasing. It will tend to 0 as x tends to infinity. As x tends to 0, it tends to 1. But in the neighborhood of x equal to 0, in the neighborhood of x equal to 0, sine x by x is greater than 0 but less than 1, as you can see. This is sine x by x for any x in the neighborhood of x equal to 0. It's less than 1 but greater than 0. Less than 1 but greater than 0. Right? So, as x tends to 0, sine x by x tends to 1 from the less than 1 side, because sine x by x is always less than 1. So we say sine x by x is coming closer and closer to 1, but will maintain values less than 1 all the time. So sine x by x tends to 1 from the less than 1 side. This is what less than 1 side. Yes or no? Got me? Now, can I wipe this off? Huh? If I have to talk of if I talk of, say, limit box of sine x by x, box of sine x by x, x tends to 0. Box is the greatest integer function. Right? Box is the greatest integer function that we have discussed. Now, in the neighborhood of x equal to 0, as you have seen, this is 1. The value at any given x, the value of sine x by x is less than 1. Right? In the neighborhood of x equal to 0, sine x by x is less than 1. Right? So, very close to x equal to 0, be it to the left of x equal to 0 or to the right of x equal to 0, sine x by x lies between 0 and 1. So, box of sine x by x does not tend to 0, it is identically equal to 0. It is identically equal to 0. So, wow. So, this limit will be 0. Why? Because around x equal to 0, sine x by x lies between 0 and 1. Box of this will be identically equal to 0. So, limit box of sine x by x as x tends to 0 would be 0. No. 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 I never said box of x by y is box of... Oh, you're saying box of this by x. But n, that's a natural number, not a real number, right? Clear? Sin x by x, sorry, this is not by 2, this is by x, by x. Sin x by x lies between 0 and 1, box of sin x by x will be 0. So, if you have to draw the graph of box of sin x by x, hello? Box of sin x by x only very close to x equal to 0. Then it will be undefined at x equal to 0. But in the neighborhood of x equal to 0, it will be identically equal to 0. In the neighborhood of x equal to 0, box of sin x by x will be identically 0 and undefined at x equal to 0. But the limit exists. Limit will be 0. Yes or no? Hmm? And if I said limit fractional part of sine x by x as x tends to 0. Hey, because yes, 1. You could have also written this as sine x by x minus box of sine x by x. This limit exists, this limit exists. So limit of the, and both are finite. So limit of the difference will be difference of the limits. So this is going to be 1 minus 0, which is going to be 1. Yes or no? Clear? Will be infinite. Will be not a finite limit. No, 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 it will not. So if you had, say, limit sine 3x by 4x as x tends to 0. If you had limit sine 3x by 4x as x tends to 0, where x is in radians, see, it's like limit. The way to you read that limit is limit sine of something by something. As that something tends to 0, that's 1, right? So now in this case that something is 3x, so you should have a 3x here. So what you do is 1/4 limit sine 3x by 3x as x tends to 0 is the same as 3x tends to 0 into 3. So that's good. This is going to be 1. Sine something by something as that something tends to 0, that's going to be 1. So this is going to be 3 by 4. That's going to be 3 by 4. If I had limit 1 minus cos x by x squared as x tends to 0. This can be written as 1 minus cos theta is 2 sine squared theta by 2 by x squared as x tends to 0. Right? Yes. So this can be written as limit 2 sine x by 2. So this is the subject. So the subject here should be x by 2 whole squared. And then, so I have an x squared, so I balance this with a 4. This 4 managed here. X tends to 0. Sine theta by theta whole squared as theta tends to 0 is going to be 1. So that makes it half. That makes it half. Suppose I had limit root 1 minus cos 2x by x as x tends to 0. Suppose I have this. This is limit root 2 sine squared x by x as x tends to 0. No, no. This is actually limit. The root 2 will come out. Mod sine x by x as x tends to 0. Root sine squared x is not sine x. Mod sine x is mod sine x. Root sine squared x is not sine x. It is mod sine x. So then, to the right of x equal to 0, sine x will be positive. So mod sine x will be sine x. When x is slightly less than 0, sine x will be negative. So mod sine x will be minus sine x. Yes or no? So I'll have to look at the left hand limit and the right hand limit at x equal to 0. So then, let me look at the left hand limit. Limit as x tends to 0. From the less than 0 side, when x is slightly less than 0, sine x is negative. Mod sine x therefore would be minus sine x. And this is going to be 1 minus 1. So this makes it minus root 2. That's the left hand limit at x equal to 0. The right hand limit of the same x tends to 0 from the greater than 0 side. When x is slightly greater than 0, sin x is positive. So mod sin x will be sin x, and this will be rendered sin x by x. So that's root 2. So left hand limit is minus root 2, right hand limit is root 2. So the limit does not exist because left hand limit is not equal to the right hand limit at x equal to 0. The limit does not exist. Right? Can I wipe this off? Now, suppose I had limit 1 minus cos x root cos 2x by x squared as x tends to 0. 1 minus cos x root cos 2x by x squared as x tends to 0. Now what is not allowed is the following. You would say, all right, let's do this. As x tends to 0, root cos 2x tends to 1. So this limit is equal to limit 1 minus cos x by x squared as x tends to 0. Smart ass. This tends to 1 and you did this. And then you say, all right, this is 2 sine squared x by 2 by x squared as x tends to 0. On your way to victory, limit sine x by 2 by x by 2 whole squared by 4 as x tends to 0. Half. This would be 1 sine theta by theta whole squared, theta tends to 0, and this you say is half. No, that is not allowed. This is not allowed. You applied limits on this and gave stepmotherly treatment to the rest. Right? Not accepted. What you will have to do here in this case is,
But it's product of two limits you can take, that limit root over cos 2x.
is this limit product of two limits, Sasure?
So we can do 1 minus cos x by
Oh, so you want to say, okay, so let's look at what he's saying. He's saying, all right, this is limit 1 by x squared minus cos x by x squared root cos 2x, right? As x tends to 0. And this, he says, is limit 1 by x squared as x tends to 0 minus limit cos x by x squared root cos 2x, right, Anshul? Thanks. Glad you didn't allow me to expose you further. Is that okay? Yeah. So this is not finite, isn't it? This is not allowed. All of this is illegal. Don't, right? So what you need to do, let's say, I rationalize the numerator. Okay? So on rationalizing the numerator, as x tends to 0, right? I rationalize the numerator by multiplying numerator denominator with this, right? Now let me look at just the numerator, simplify this. 1 minus cos squared x cos 2x is 1 minus cos squared x. Cos 2x is like a 2 cos squared x minus 1. Yes or no? Right? Which then is like a minus 2 cos to power 4x plus cos squared x plus 1. Yes or no? Right? Now what I can do is, see, at cos squared x equal to 1, this expression is becoming 0. Do you see that? If you put cos squared x equal to 1, this is 1 into 2 minus 1, 1, 1 minus 1, 0. This expression is becoming 0 at cos squared x equal to 1. That means cos squared x minus 1 must be a factor of this. If this is becoming 0 at cos squared x equal to 1, that means if I factorize this, cos squared x minus 1 must turn out to be a factor of this. Right? So what I do is, I do like a minus 1 and I do like a 2. So that 2 minus 1, the one that was originally there, is taken care of. I force a cos squared x minus 1. This then is like a 2 into 1 minus cos to power 4x plus cos squared x minus 1. Yes or no? Clear? And the expression then, if I took like a 1 minus cos squared x common from this expression, then what I am left with is 2 into 1 plus cos squared x minus 1, isn't it? This is what I am left with on taking 1 minus cos squared x common from this, which is like sine squared x into 1 plus 2 cos squared x, right? So now, good for us. All look good. This numerator becomes sine squared x into 1 plus 2 cos squared x divided by x squared into 1 plus cos x into root cos 2x. Yes or no? As x tends to 0, this is sin x by x whole squared. This will tend to 1. As x tends to 0, this will tend to 3. 2 plus 1, 3. This will tend to 2. So that makes it 3 by 2. That's the limit. What did we get earlier? Half. Then we made a mistake. Clear? Ask. Okay, that's all right. If you mean it, you can still ask. Okay, then that's okay. Can I wipe it off? Huh? Now, in fact, some series, regular series, which I want you to know, when x is in radians, I'll keep introducing more and more, but for the time being, the following would suffice. The expansion for sin x is given by x minus x cubed by 3 factorial and so on and so forth. Cos x is given by 1 minus x squared by 2 factorial e power x and ln 1 plus x by 2 naught factorial this expansion is given only when x is greater than minus 1 but less than or equal to 1. These are some expansions that you must know. All right. Now, look at this first one. If I divide x throughout, then sin x by x turns out to be 1 minus x squared by 3 factorial plus x power 4 by 5 factorial and so on and so forth. Right? So, as x tends to 0, this tends to 1, isn't it? Because all of the terms go into oblivion. Right? So, limit sin x by x as x tends to 0 from this series is also 1. Right? Which of course we established more authentically using sandwich theorem. Clear? Yes or no? Now, e power x, look at this. E power x minus 1 divided by x is 1 plus x by 2 factorial plus x squared by 3 factorial and so on and so forth. Even though as x tends to 0, numerator tends to 0, denominator tends to 1, but the ratio comes closer and closer to 1. Right? Limit e power x minus 1 by x as x tends to 0 then turns out to be 1. Another standard limit. Although let me tell you, giving you a proof of these limits using series expansion, I'm actually diluting matters a little bit. This is not authentic at all. But for the time being, let's take it this way. The real proof of this is a lot more intricate, which will mess you up if I offer it right now. But for the time being, it's only a makeshift arrangement. Okay. But then this is a standard limit in any case. Limit e power x minus 1 by x as x tends to 0 is 1. A brother of this limit, if a is a positive number, right, then any a, realize, can be written as e power log a. Do you realize this? Any positive number a can be written as e power log a. How many of you don't understand this? Okay. Reason this is true is if you take log of this will give me log a. If you took log of this, then this will give me log of e power log a, which is like log a, log e. But log e is 1, so this turns out to be log a. Log of this is the same as this, so the two must be equal. Got me? And why positive? Because logarithm will not be defined for a negative number. Right? So then, a corollary of this result, limit a power x minus 1 by x as x tends to 0. This a I write as e power log a. This a I have written as e power log a whole to power x, therefore e power x log a minus 1 by x as x tends to 0. Now, after all, what's the limit? The limit is, the way to read this limit is limit e power something minus 1 by something as that something tends to 0, that must be 1. Now, what is the something here? X log a. But what is it that we have here? X. So, I should bring in this something here, log a, and then balance it outside, log a. So, now, as x tends to 0, obviously, x log a also tends to 0. So, e power something minus 1 by something as something tends to 0 is 1. So, this leaves you with log a. This leaves you with log a. Right? So, this is another standard limit. Another standard limit. Can I wipe it off? Now, ln 1 plus x, like I said, is x minus x squared by 2 plus x cubed by 3 and so on and so forth. Ln 1 plus x by x is like 1 minus x by 2 plus x square by 3 and so on and so forth. Now, limit ln 1 plus x by x as x tends to 0. As x tends to 0, all these terms will vanish. You are left with 1. So, this is equal to 1. Another standard limit. Ln 1 plus x by x as x tends to 0 is 1. So, if I had limit ln 1 plus bx by x as x tends to 0. Yes, b. So, ln 1 plus something by something, and that balanced here. So, this would be 1 as x tends to 0, bx also tends to 0. So, this is going to be b. Right? As long as x square lies between minus 1 to plus 1. That's the only limitation. And when x tends to 0, obviously x square will lie between minus 1 and plus 1, isn't it? Suppose I had e power sine 3x minus e power sine x by x as x tends to 0. All right. Let me first goof up matters here. Okay. Let me goof it up. Create a mess of this limit. Okay. Let me do the following. Let's say this is limit e power sine 3x by 3x into 3x minus e power sine x by x into x divided by x as x tends to 0. So far no problem. This I can do. And now I say, hey, sine 3x by 3x as x tends to 0 is 1. So then I say this tends to 1, so this will be e power 3x power x by x as x tends to 0. Right? And then I say this is e power 3x minus 1 minus e power x minus 1 by x as x tends to 0. Right? Right now? 3 for this limit. So e power something minus 1 by something as something tends to 0, that's going to be 1. So this is going to be 3. E power x minus 1 by x as x tends to 0, that's going to be 1. So this is going to be 3 minus 1, 2. Jabardast. Right? সুপ্রিয় কি ছিল সুপ্রিয় বাবুল সুপ্রিয় राइट कॉलर अप अरे तुम शिफ्ट कैसे हो गए तुम तो वहां बैठे थे लेटरल शिफ्ट हुआ तुम्हारा हाँ वो ब्रेक में हो गया तुमको डिस्प्लेस किया या तुम शिफ्ट हुए डिस्प्लेस किया, वही तो। और तुम बाल बच्चे वाले आदमी हो, तुम ज्यादा पंगा नहीं लेना चाहते हो। ठीक है भैया, हट जाते हैं शांति से। See, this is all crap that I have done here. Okay. This I took as 1 and this I left unattended. This I took as 1, this I left as unattended. Right? This is not permissible. Right? This is not permissible. So what we need to do here is the following. So this is all wrong. This is all wrong, right? So let's look at what is right. This I write as, hello, limit e power sine 3x minus 1 by x minus e power sine minus 1 by x as x tends to 0. Now, let me assume for the time being that this limit exists. And both these limits also exist. Then the limit of the difference will be difference of the limits if both limits exist. This is e power sine 3x minus 1 by x as x tends to 0 minus limit e power sine x minus 1 by x as x tends to 0. How about it? Now, there was an x here. I bring in a sine 3x because this is my subject for the limit. E power something minus 1 by something. As x tends to 0, sine 3x will also tend to 0. And there was an x here. I balance this sine 3x. Yes or no? Right? Now, this is sine theta by theta. So I should have a 3 here. So that theta by sine theta is theta tends to 0. And this 3 I balance with a 3 here. Right? Same here. As x tends to 0, sine x tends to 0. So e power something minus 1 by something. X by sine x. So does not mean if you get the same answer that was right. Okay. you could make an even number of mistakes and get the right answer, right? Even number of mistakes. Why? Because you made a mistake here, you made a mistake here. 2 mistakes, right? That's why the answer will turn out to be the same. It might, right? So then this is like, this will tend to 1, this will tend to 1, so this will be 3 minus, this will tend to 1, e power something minus 1 by something, something tends to 0, that's 1, 3 minus 1, that makes it 2. Right? Clear? Sounds all right? All's good so far? Now, another standard limit. Say n is a natural number. Right? Say n is a natural number.
So in the last case, you told that let the limit exist. So how will understand the limit exists?
No, I mean, if the limit exists, then all of this will be true. Right?
So we don't have to check if the limit exists.
If it comes consistent at the end, it exists. If there is consistency. Now, let me look at this. Limit x to power n minus 1 by x minus 1 as x tends to 1. Now this limit is also numerator tending to 0, denominator also tending to 0. It's undefined at x equal to 1, right? First of all, x power n minus 1 is this an identity? Why? Why is this true? The point is, why is this true? Why is this true? Why is this true? Be simple. Don't beat about the bush. Yeah, shabash. This is a GP series 1 plus x squared plus x power n minus 1. That's this divided by this, isn't it? What? The sum of this GP series is x power n minus 1 divided by x minus 1. Yes or no? That's it. It's true. Clear? So this is like limit x minus 1 into 1 plus x squared plus x power n minus 1. Right? So x minus 1, since x is not equal to 1 anyways, it's about the neighborhood, so x minus 1 is not 0 and therefore a cancellation is fine. Right? Right? So as x tends to 1, 1 plus 1 plus 1 plus 1, n times, that makes it n. That makes it n. Yes or no? Another standard limit. X power n minus 1 by x minus 1 is going to be n. Right? Clear? Similarly, minus a to power n divided by x minus a as x tends to a. Now this I could have written as, I can take a to power n common, I could have taken a common, yes or no? As x tends to a, x by a tends to 1. Right? So this is like t to the power n minus 1 by t minus 1 as t tends to 1, isn't it? See? Limit t to power n minus 1 by t minus 1 as t tends to 1 is going to be n. That's what we obtained a little while ago. T to power n minus 1 by t minus 1 as t tends to 1 is 1. Is n, sorry, this is going to be n, right? This part is going to be n. That's straight out of the previous limit. Right? T is x by a here. So this is like n a to power n minus 1. If you had limit x power m minus a power m divided by x power n minus a power n as x tends to a, then this can be written as x power m minus a power m divided by x minus a, x power n minus a power n divided by x minus a as x tends to a. This is going to be m by m a to power m minus 1 divided by n a to power n minus 1. Right? क्या? So this is 0, this tends to 0, this is also tending to 0. But that doesn't mean that the ratio will tend to 0, isn't it? In x power n minus 1 by x minus 1, the numerator and denominator both tend to 0. Numerator is not identically 0. It only tends to 0. That's clear? Now, let me also mention to you some facts, and I'm going to throw light on those things later on, but two important things. One, see, you know the graph of log x. This is the graph of log x. As x tends to 0 from the greater than 0 side, log x tends to minus infinity. Right? As x tends to 0 from the greater than 0 side, log x tends to minus infinity. As x tends to infinity, log x tends to infinity. Log x becomes larger and larger and larger. As x tends to infinity, log x becomes larger and larger and larger. Log x tends to infinity. Now, this one, of course, I would require, you would be requiring more of explanation on this, but for the time being, if I have log x by x, as x becomes larger and larger and larger. See, as x becomes larger and larger and larger, numerator becomes larger and larger and larger, denominator also becomes larger and larger and larger. But we'll be able to understand this one fact in times to come. As x becomes larger and larger, log x increases always faster than log x. Any positive power of x will always increase faster than log x. And this limit will turn out to be 0. Because both numerator and denominator tend to infinity, but denominator will increase faster than numerator. So, one fact that you must remember, log x, any positive power of x, integral power of x, will increase faster than log x. Second, e power x will always increase faster than any positive power, integral power of x. Which means if I had limit x power n by e power x as x tends to infinity, this will become larger and larger, this will become larger and larger, but e power x will grow faster, and this limit will also turn out to be 0. Yeah, but see, I have not told you that increasing decreasing functions here. So yes, 1 by x, and that will be 1. So for x greater than 1, 1 by x will be smaller. So its increase is smaller. But that's why I reserved these remarks for a later stage, because these are not things that I have covered yet. So this is another fact that you must bear in mind. X power n by e power x as x tends to infinity will always be 0. Now, see, limit ln 1 plus x by x as x tends to 0 is 1. Right? What this means is that as x tends to 0, ln 1 plus x by x tends to 1. This is what it means. Right? This is what it means. That means ln 1 plus x, this will go in the power. The power 1 by x would tend to 1 as x tends to 0. Right? This 1 by x will appear in the power here. Properties of logarithm. If log of a number tends to 1, then that number must tend to e. 1 plus x to power 1 by x must tend to e. Right? Which means as x tends to 0, 1 plus x to power 1 by x will always tend to e. That means I can write 1 plus x to the power 1 by x as x tends to 0 is e, another standard limit. Right? Now, if you say x is 1 by n, then as x tends to 0, n would tend to infinity. Then this limit transforms to limit n tends to infinity 1 plus 1 by n whole to power n, and that must be equal to e. Remember when I was doing binomial theorem, one thing that I told you that this expression will always lie between 2 and 3. But as n becomes larger and larger, it becomes equal to e, which is a number lying between 2 and 3. Right? Now, a limit of the form 1 to the power infinity. See, these were limits of the form, say 0 by 0. You know, now there are times when you have a limit of the form 1 to power infinity. For example, you know, we've already dealt with one limit of the form 1 to power infinity is e. This is, as x tends to 0, this tends to 1 and this tends to infinity. So we say it's a limit of the form 1 to power infinity. That's a form of this limit, right? Now, a generalization on this. Limit fx to the power gx as x tends to a, where as x tends to a, fx tends to 1 and gx tends to infinity. Fx tends to 1 and gx tends to infinity, right? Is it not this form? Fx tends to 1 and gx tends to infinity. Now, a more generalized form. Fx to power gx, fx need not be 1 plus x and gx need not be 1 by x. As x tends to a, we need to evaluate this, right? Now, fx, we are assuming it's positive in the neighborhood of x equal to a, can be written as e power log of fx. This then is like limit x tends to a, e power log fx into gx. Right? Now, this log fx, I could have written as log fx minus 1 plus 1. Could I do this? Why not? Fx minus 1 plus 1 is fx only. What has set you thinking so hard? right? So this is like limit x tends to a e power log fx minus 1. What I do is, see, as x tends to a, fx tends to 1. So fx minus 1 tends to 0. Remember this limit? Limit ln 1 plus z by z as z tends to 0 is 1, right? So I want to bring it to that form, ln 1 plus z. So I divide by z. What is my z here? fx minus 1, which tends to 0, right? Into fx minus 1 into gx. I balance this. Right? As x tends to a, fx minus 1 tends to 0. So ln 1 plus z by z as z tends to 0, that's going to be 1. This is going to be 1. So assuming this limit exists, then limit in this case can get onto the power because of continuity considerations. This then becomes 1. This will tend to 1. And what remains is just this then, because this will tend to 1. What remains is just this product. Ln 1 plus z by z as z tends to 0. Z tends to 0. fx minus 1 tends to 0. E power fx minus 1 into gx. 1 plus z by z ln 1 plus z by z where z tends to 0. That's 1, isn't it? No, but then I'm applying the limit to this also. It's like this is limit of this into limit of this. If the limit exists, then it's going to be limit of this into limit of the product will be product of the limits if the limit exists. If the limit does not exist, then of course no point. If the limit exists, then I can do limit of the product will be product of the limits if each of these limits exists and are finite. This exists and is finite. If this entire limit had to exist, then this limit should have also existed and should have been finite. So I could deploy this. So this is another standard result you want to remember. If fx tends to 1 and gx tends to infinity, as x tends to a, then limit x tends to a fx to power gx will be x tends to a e power fx minus 1 into gx. G tends to infinity. It was not tending to 0.
No, ln 1 by z by z, z tends to
Huh.
0. So, but here is limit x tends to a, but fx tends to
Agreed. X tends to a, which means fx minus 1 tends to 0. Because fx tends to 1. So ln 1 plus z by z as z tends to 0. fx minus 1 is my z. As x tends to a, fx tends to 1. So fx minus 1 tends to 0. Right? So ln 1 plus something by something as something tends to 0. That's going to be 1. Right? We will you mentally done for day, I guess, for the day, right? Stand back.